Alright, so now we're going to be working through a review of everything we just covered. And all of these questions are going to be AP level, so if you are a little bit lost, don't worry, that's completely normal. So first we have f of negative 5. So this is negative 1. We have negative 2, negative 3, negative 4, and this is negative 5. So f of negative 5 will be right here. This is 1, 2, 3, 4, 5, 6. So the answer to this one is 6. Then we have f of 2, 1, 2. We use the filled in dot right here, not the whole, when we're doing when we're evaluating functions. So this is going to be 1. F of 4 is going to be 3 and then 4. And we can see there's a point right here. This is negative 1, negative 2, negative 3. So this answer is negative 3. Then we have limit as, now we have our first limit as x approaches negative 7. This is negative 6, and then this is negative 7, so it's going to be this whole right here, so that's going to be at 2. Then we have limit as x approaches negative 5, which is going to be up here, which is 6. Then we have limit as x approaches 2 of f of x, which we're going to be using the whole right here, because we're approaching from the left and from the right. We hit this whole, so we get 3 for this one. Then the limit as x approaches 4. As you can see from the left side, we're approaching 2, but from the right side we're approaching negative 3. So that means that the limit is going to not exist. So D and E for does not exist. Then we have the limit as x approaches 0 of f of x. As we can see, it approaches 2 different ways too, so this is going to be D and E. There's a vertical asymptote there. Limit as x approaches 0 from the left side. So as we approach 0 from the left side, we're approaching negative infinity. And then limit as x approaches 0 from the right side, so as we're approaching from the right side, we approach positive infinity. Then we have the limit as x approaches 4 from the right side, so from the right side, we're going right here, this is negative 3, so negative 3. Then from the left side, we approach this whole right here, which is at 2, so we're going to put a 2 here. Then we have the limit as x approaches, you can't really see that well, this is the limit as x approaches negative infinity. So that's going to be approaching 0, as you can see. As it keeps going to negative infinity, the function approaches 0. And then same for this one, this is infinity. So as we keep going to infinity, it also approaches 0. So we can put a 0 for that one. Alright, so now we're going to use definition of continuous function. So let's review. For a function to be continuous at, let's say, at x equals a, the first condition is that f of a needs to be defined, and we went over this previously, but I'm just going to do a quick review. F of a needs to be defined. The limit as x approaches a of f of x needs to exist. And finally, f of the function evaluated at a needs to equal the limit as x approaches a of f of x. So if all these three conditions are met, then the function is continuous. So the first question asks, f is not continuous at x equals negative 7. Well, let's look at negative 7. So the limit does exist because it approaches that whole, but the function is not defined at that part. So we can say, because f of negative 7 is not defined. Alright, now f is not continuous at 2. So the limit does exist right there, and then the function is defined because it goes to right there, but the function value is 1 and the limit value is 3, so the function value, so we can say f of 2 does not equal the limit as x approaches 2 of f of x. And then finally, not continuous at, that's the 4. So let's look at 4. As you can see, the limit from the left doesn't equal the limit from the right. So we can either say that, or we can just say the limit doesn't exist. And I'm just going to say the limit as x approaches 4 of f of x does not exist. There we go. Moving on. So now we're going to actually be solving the limits. For this first one, we can just use direct substitution. So you have negative 2 squared, and remember this 2, the negative is not being squared, just the 2, plus 4 times 2. So if we evaluate that, that's going to be negative 4 plus 8, which equals 4 as our final answer. Alright, for this next one, the thing is, okay, I'm going to give you guys a little tip for limits. So as you can see, this negative sign might look like we have to do something different, but you don't. And I'll show you why. If you plug in the limit, I would always start by plugging it in. So if we plug in the 9, we get square root of 9 minus 3 over 9 minus 9, which equals 0 over 0, right? So if you get 0 over 0, that means there's going to be a hole there. The function's 0, 0 is indeterminate. So that means we can do any of our normal limit stuff that we've been doing. We don't have to like do the 8.99 thing. It's not a vertical asymptote, basically. So we can just multiply this one by the conjugate. So multiply by square root of x plus 3 over the square root of x plus 3. So square root of x times square root of x is just x. Square root of x times 3 is 3 root x, but then we subtract 3 root x after we do that. So then we just do negative 3 times positive 3, which is minus 9. So we can put that. And then on the bottom, we don't have to FOIL this part out because we're almost done. I'll go ahead and write the limit down just so we're not lost. So limit as x approaches 9 from the negative direction. And then when we FOIL it out again, we get x minus 9. And then on the bottom, I won't FOIL it out, so we just get x minus 9 times square root of x plus 3. And then x minus 9's cancel out. So now we can just plug in our limit into here, so we get 1 over root 9 plus 3, which root 9 is just 3, so 3 plus 3 is 6, so we get 1/6 is our final answer to that one. Alright, now we have the limit as x approaches 0 of x over tan x. Remember, this is a unit 1 review, so we're not going to be using L'Hopital's rule because some people might not be there yet. But what we are going to be doing is we're going to be turning tan x into sine x over cosine x. So we can turn, because you should know that from pre-calc. So after we do that, we can flip the keep change flip. We can make it turn into x cosine x by multiplying by the reciprocal over sine x. Now what we can do is, the thing about limits that's special with limits and not with derivatives or integrals is the limit of the products equals the product of the limit. So what we can do is we can turn the limit into two limits. So we can do the limit as x approaches 0 of x over sine x multiplied by the limit, and I don't have much room here, but I'm going to try to fit it in, of cosine x. So now we should know that this limit evaluates to 1. That's one of our special trig limits. And this one we just plug in cosine of 0, which is 1. So 1 times cosine of 0 is 1 as our final answer. Alright, moving on. Now we have a vertical asymptote, and you can see how even this one is different than this one, because if you plug in negative 2, we get negative 2 over negative 2 plus 2, which equals negative 2 over 0. And since this is not 0 over 0, this is a number over 0, so it's going to be a vertical asymptote. So what we can do with that is we can plug in a number, we're approaching 2 from the positive direction, so we can plug in a number a little bit greater than 2. So what I'm going to do is I'm going to plug in negative 1.999, which is a little bit greater than 2. And we're going to divide by negative 1.999 plus 2. And that's going to equal negative 1.999 over 0.001. And then that's going to approach negative infinity, because this evaluates to a negative number. And this closer and closer you get to 2, the smaller and smaller this will go. So that's our answer for that one. Now for this one, I'm going to bring the 1 plus outside the limit, because the limit of the sum is the sum of the limit. So I can just do 1 plus the limit as x approaches 0 from the negative direction of 1 over x. So now now what I can do is I can plug in a number really, really close, but just a little bit less than 0. So I can do 1 plus 1 over negative 0.001. So this part right here is going to approach negative infinity, right? Because this evaluates to negative. And negative infinity plus 1 is still negative infinity. So this limit will approach to negative infinity. For this one, we can just do direct substitution. So sine of pi times 1 is just sine of pi, which, using our unit circle, evaluates to 0. Alright, our next one, we have a limit as x approaches infinity. For these types of limits, we're only going to look at the greatest term. So for whichever term is increasing the most. So for this one, limit as x approaches infinity, we're going to use negative 6x to the fifth over x. So I can simplify this if I want. So we have limit as x approaches infinity of negative 6x to the fourth. That's not a 4, that's a square. Negative 6x to the fourth. And now I can see that this evaluates to negative infinity, because if I plug in an infinity, this will just be a big number, and then the negative will make it negative infinity. That's it. Alright, so for this next one, we're going to do the same thing. It tries to throw you a loophole with t, but it doesn't really matter the variable. This one's to negative infinity, though, so we might have to be a little bit careful. But let's solve this. So we got negative t cubed over 7t cubed. Alright, the t cubes cancel out. So now we have the limit as t approaches negative infinity of negative 1/7, and then that's just negative 1/7 because there's no t left. So that's our answer. Alright, so now we have the limit as x approaches negative infinity, and we're going to use the biggest term, so we have x over x squared. So now what we can do is we can simplify this. I mean, you might be able to see what the limit is already, but I'm just going to do it for the people who can't. And then when we plug in infinity or negative infinity, it doesn't matter. 1 over infinity is always 0. So we can just say this is 0. And that's our answer. Alright, for this next one, this is one we have to be careful at. This is not a rational function. So what we're going to do is we're going to do limit as, I'm going to rewrite the limit y approaches negative infinity. And we're going to still use the biggest term. So we have negative y is the biggest in the numerator over, and we can use the biggest term inside the square root. So I'm just going to put the square root, I'm going to write 6y squared. Alright? Now if I simplify the denominator, I can do the limit as y approaches negative infinity of negative y over root 6. Now be careful with this one. The square root of y squared is the absolute value of y. So you can't just cancel this out like you normally would. Since we're approaching negative infinity, if we plug a negative infinity into this bottom number, it's going to become positive. If we plug a negative infinity into this top number, it's also going to become positive. So it's going to be, the answer is going to be positive. And once we know that the answer is going to be positive, we can just not think about the y's because they're the same degree. So then we know the answer will be 1 over root 6, not negative 1 over root 6. Alright? Let's move on. So for this one, we just have to check that the limit from the left equals the limit from the right, and then we can plug in our values. So, and then if they're equal, that's going to be our answer. So let's check the limit from the left of f of x. We get 2 squared minus 3 times 2 plus 6. 6 minus 6 cancels out, so we just get 4. Alright, so now let's check the limit as x approaches 2 from the right side of f of x. We get negative 2 squared plus 3 times 2 plus 2, which is, that's negative 4, plus 2, that's negative 2 plus 6, that's also going to be 4. So that means the limit as x approaches 2 of f of x equals 4, since it's 4 from the left and 4 from the right. Alright, for this one we're going to have to, it's a little weird because there's no numbers, but we treat it just the same. So we have the limit as x approaches negative a. And obviously if we plug negative a into here, we get 0 over 0, so that means we can do more work to find the limit. Remember, always use direct substitution first. If you get a number of 0, then it's a vertical asymptote. If you get 0 over 0, it's a whole, and if you get a number, then that's the answer, assuming it's a continuous function. Alright, so let's factor the top using difference of two squares. So we get x plus a times x minus a. And then now let's factor the bottom. We get x squared plus x squared minus a. So we can factor the x squared minus a into x plus a. And if you don't understand that, I would encourage you to review a bit of factoring rules, but this is what it factors into. So now the x plus a's and the x minus a's all cancel out. So now we just have the limit as x approaches negative a of 1 over x squared plus a squared. So now if we plug negative a into here, we get 1 over a squared plus a squared, because negative a squared is a squared, and that's equal to 1 over 2a squared, and that is our final answer. All right, moving on to page 3. Now we're getting into the more AP level questions. Find a c such that f of x is continuous when on the entire real line. So for this one, we need to make sure that the limit from the left equals the limit from the right, so that way it's continuous, right? So first we need to we're going to set these equal to each other and plug in 4. So we get 4 squared equals c over 4. And then solving for c, we get c equals, this is 16 times 4. 16 times 4 is 64, so c equals 64 is our answer. Alright, for this one, find and label all the discontinuities. So for this one, when we're finding discontinuities, we always factor out the entire thing. So I can factor this into x, 2 times x plus 3, and then I can factor out a 2 out of the denominator. That'll give me x squared plus 9, so that can be factored using difference of 2 squares, x plus 3 and x minus 3. X plus 3's cancel out, and we are left with and we're left with 2 over x, or the 2's also cancel out, so we're just left with 1 over x plus 3. So now since these canceled out, this is a whole. So we have a whole, or a removable discontinuity at x equals negative 3, and we have a vertical asymptote at x equals 3. And that's our solutions. Alright, determine all the vertical asymptotes. So again, we're going to factor. We can't just set the denominator equal to 0 because we might end up with a whole, right? So I'm going to factor the denominator, and the x minus 2 cancels out. So then we get 1 over x plus 2. So there's a vertical asymptote when x plus 2 equals 0, which is that x equals negative 2. And that's our answer. Alright, true or false? If f is undefined at x equals c, then the limit of f of x as x approaches c does not exist. Well, that's not true, because we can have something like this. We can have it approach a whole. F is undefined at here, but the limit does exist because it approaches the same place from both sides. This is going to be false. True or false? Limit as x approaches c of f of x equals L, then f of c equals L. Well, that's not true either. We can have something like this, where if it approaches, like f of this would be right here, but then the limit would be right here, which is not the same. So this is also false. Alright, the graph of the function f is shown to the right. Which of the following statements are true? X equals a is in the domain of f. Well, yes, it is in the domain, because if we plug it into a, we do get a value for f. It's not continuous there, but it is in the domain, so I'm going to put a little check mark. Limit as x approaches a from the right side equals limit as x approaches a from the left side. Well, we can see that, yes, they do both approach this whole right here. So this is also true. And then for c, limit exists. Well, if they approach the same place from both sides, then the limit does exist. It's not equal to f of a. That's true, because f of a is defined right here, and the limit is defined right here, so that's also true. F is continuous at x equals a. That's not true, because the limit does not equal the function value, which is one of our definitions of continuity. Alright, so now we have a pretty long limit, which is going to be really helpful to know how to solve when we get to derivatives, but this might show up on a Unit 1 test. That's why we are covering it. So we have the limit as delta x approaches 0, and I'm going to just expand out everything. So we get x squared plus 2 times x times delta x. I'm just going to write the x first so that you don't get confused, plus delta x squared minus 2x minus 2 delta x plus 1 minus x squared plus 2x minus 1. Yes, this is a really long equation right here. Basically what we did, I distribute this negative, I distribute this negative 2, and I FOILed out that. So now let's cancel some out. So negative 1 and positive 1 cancel out. 2x and minus 2x cancel out, and then negative x squared and x squared cancel out. So now we have the limit as delta x approaches 0 of what we have left is 2x times delta x plus delta x squared minus 2 delta x over delta x. So now we still can't plug in our limit, because if we plug in delta x at 0, then we're going to end up with 0 over 0 again. And obviously that's not what we want. So now what we're going to do is I'm going to factor out a delta x out of everything on the top. So limit as delta x approaches 0. I'm going to take this delta x out. I'm going to have 2x plus delta x minus 2 over delta x. So now these delta x's cancel out. So now we can just plug in 0 for delta x and we get 2x minus 2 as our final answer. There we go. Alright, on the graph, draw a function that has the following properties. F of 5 equals 6. So I'm just going to do this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. F of 5 equals 6 is going to be right here. And then it has a jump discontinuity at x equals 5, so I'll just do like a hole here, and then I'll do like an arrow here, and then an arrow here, and that should be good. Obviously, graphs are going to vary between whoever's doing it, so yeah. Create a function such that the limit as x approaches 5 does not exist because it is approaching positive infinity from both the left and right sides, so both the function and the graph. So let's show the graph first, what it would look like to make it easier. So this is 1, 2, 3, 4, 5. So if it's approaching positive infinity from both sides, it would approach positive infinity like that, and then positive infinity like that. So a function that would look like that is 1 over x minus 5 squared, because when you square it, it means they're approaching the same place. But the limit still doesn't exist because you get 1 over 0, which is d/e, or a vertical asymptote, which we can see is a vertical asymptote right here. Alright, find a function such that f of x has a hole at x equals 7. So a hole at x equals 7 means that x minus 7's cancel out with the numerator and denominator. So we can do something like that. And a vertical asymptote at x equals negative 4. So we can put our x plus 4 in the denominator like that. Now, I don't know if they want us, so this is the right answer, but let's assume that this is multiple choice and this is not on the answer key, or on the multiple choice answers, so let's just FOIL this out. So we get x squared minus, so that's 4x minus 7x, that's minus 4x minus 7x minus 3x, plus minus 28, I think. Yeah, that should be right. Alright, yeah, because that factor is right. Okay, so that's going to be our answer for that. Now let's move on to the calculator portion. Alright, so here we are on the calculator portion. So what you're going to need to do for this one is you're going to need to grab out your calculator. You're going to go to y equals, and you're going to do x, you're going to put this function into y equals. So x squared over x minus 2. And then you're going to go to vars and y bars in function, and then you're going to hit y1, you're going to open up a parentheses, and you're going to put in all these values. So first you're going to put in 1.9, and I got negative 36.1. Then I'm going to do the same thing, but I'm going to put 1.99 in, and I get negative 396.01. Then I'm going to do the same thing again, but with 1.999, which is negative 3996.001. So I can already, and then if I plug in 2, obviously if you plug in 2, it's undefined. So I'm going to write UDF for undefined. So now I can already see it's approaching negative infinity from the left side because it's getting really close to negative infinity. But let me do it from the right side too. So let me do the same thing and plug in 2.1, and we get 44.1. And then let's do 2.01, and we're at 404.01. And now let's plug in 2.001, and we get 4004.001. So now it looks like it's approaching positive infinity from this side, and it's approaching negative infinity from this side. So that means the limit does not exist, because it approaches two different values. Alright, for this one, what I would do is I would take out the cosine, because we know cosine is continuous. So you can just take it out and then do the limit as x approaches 0 of 1 over x. And you probably know what 1 over x looks like. It looks like this. So you can see that the limit as x approaches 0 doesn't exist, right? Because this is approaching negative infinity and this is approaching positive infinity. But if you don't know that, this is the calculator section, so you can graph it and see that. And then you would see that this does not exist. And you can also do this without a calculator by plugging a number less than 0 and seeing that approaching negative infinity, plugging a number greater than 0 and seeing that approaches positive infinity. Alright, now we are on to these questions. Find the limit as x approaches 2 of f of g of x. So first let's find the limit as x approaches 2 of g of x right here. So this is 2 right here. So we can see that it approaches a value. This is 2, 3, and 4. So it approaches a value of 4. But you see how it's approaching from the bottom? That means we need to take the limit as x approaches 4 from the left. X approaches 4 from the left of f of x. So now we can do that on f of x. So we get negative 1. This is a rule that's not commonly taught on limits, but I have seen that on tests before. So that's why I'm teaching it to you here. It's not negative 4. What am I doing? This 1, 2, 3, 4. So we approach 4 from the left right here, and we get a value of 2. So this equals 2 as our answer. Alright, now we have the limit as x approaches 1. So let's do the limit as x approaches 0 of f of x, which is does not exist. Oh, but it's 1. It should be, yeah, it does not exist. But let's just do it. Just so you know, guys, when we're doing stuff like this, we should always check from both sides, because sometimes it will work out. So let's do the limit as x approaches 1 from the left side is going to be negative infinity, and then times g limit as x approaches 1 and g of x is 3, which equals negative infinity. And then if we check the limit as x approaches 1 from the positive side, that's going to be positive infinity times 3, which is positive infinity. And obviously infinity does not equal negative infinity. The limits approach different things from both sides, so this is dne. Does not exist. Alright, final one. We have the limit as x approaches 1 from the right side of f of x. So it's f of x plus 1, so we can just do the limit as x approaches 2 from the right side of f of x. And we can see that that is, that's going to be a 3. So we can do 3 over limit as, so this is g of x plus 3, so we can just do the limit as x approaches 4 from the right side. So right here is 4, as it approaches 4 from the right side, we have negative 2. So that's equal to negative 3 halves as our final answer for that one. Alright, moving on to our last and probably the hardest question of this unit. We have a piecewise function for g of x below. Find the values for a, b, c, and d that make f of x continuous everywhere. We should use the definition of continuity and demonstrate proper notation. Alright, so for it to be continuous throughout this, it needs to be the same when you plug in 1 into here, when you plug in 1 into here, when you plug in 1 into here. Or not when you plug in, but the limit needs to be there. So if we take, so that means a has to be equal to the limit as x approaches 1 of this top part. So we can do x squared plus x minus 2 over x minus 1, which equals the limit as x approaches 1. We can factor this, we get x plus 2 times x minus 1 over x minus 1. Those cancel out, so we can just plug in the value now. So we get 1 plus, that's equal to 1 plus 2, which equals 3. So we get a equals 3. Alright, so now that's our first answer. I'm going to box it. Alright, so now 3 has to be equal to when we plug in 1 into here. So 3 equals b times 1 minus c squared. Obviously, we can't do anything with that yet because we have 2 variables. We need to get really 1 variable. So I'm just going to leave that like that for now. Let's move on. So now for 4, it needs to be 4 when we plug, these all need to be equal when we plug in 4 for here, when we plug in 4 into x from here. Obviously, there's no 4 there. And then when we plug in 4 into x from here. So we can plug into 4 into x here. So b times 4 minus c squared needs to be equal to when we plug 4 into x for there. So I'm just going to write it as d for now. And then these two need to be equal when we plug 4 into x for here. So let's do d equals 2 times 4 minus 8. So we get d equals 0. So now we can use this equation because we know b times 4 minus c squared needs to be equal to 0. And either b is 0 or c is negative 4, but b obviously can't be 0 because if b is 0, then this will automatically be 0 when it's 1, and we need it to be 3 when it's 1. So we can just set we can divide by b because we know b is not 0, so we're not dividing by 0. So we get 4 minus c all squared equals 0. So then solving for c, we get c equals -4. So I'm going to box that, I'm going to box that, and now we can finally use this equation and solve for b. So we have 3 equals b times 1 minus, and this is -4, so 1, yeah, no, this is not a -4, this is a +4, sorry, because it's 4 minus 4, yeah, it's +4, so 1 minus 4 squared, so 3 equals, this is -3 squared, so 9b, so then b equals 1/3, and that's our answer for b. So now we have a, we have b, we have c, and we have d. And that's going to do it for this review. That's actually going to do it for this entire video. I hope you like our content review and our practice problem review. And we'll see you guys with Unit 2.